Okay, thank you everyone for joining us again for the Queensland AGS webinar. This is our second one. Just a couple of housekeepings first before we start. If you have any questions during the presentation, please use the box at the bottom right of your screen to put the questions in. And at the end of the presentation, I will raise them with Adam. For those of you who don't know, if you go to the front page of the AGS website, you'll be able to see other presentations from other parts of the society outside Queensland, which we can also attend. So please look at those and see if you want to attend those. Currently, we have about one every week through to August. So tonight I'd like to introduce Adam from PAILE Solutions, talking about foundations and ground improvement system optimization. So Adam, if you have to start, please.
Yes, thank you, Chris. I'll start from sharing my screen. Welcome everyone. My name is Adam. Firstly, I'd like to thank David Lacey for giving me this opportunity to speak and present to you today. Secondly, I'd also like to give great thanks to Stephen Butling for his ongoing support, technical review, challenging questions, and fixing up my poor English language. Thank you, Stephen. I also would like to thank Bert Luke for reviewing the earlier version of this presentation. Bert was kind enough to give me good feedback and valuable comments. Today, I would like to talk to you about optimizing foundations, but I would also, in particular, I would like to focus on compression piles because the general topic is very broad. I hope that you will find this presentation interesting. So without further ado, let me move on to the next slide. Each project is different and has its own constraints, therefore it requires individual approach. There are many variables that need to be considered when choosing the right piling system, and some piling methods are more suited in particular grounds or for particular projects than others. When tendering for a particular piling contract, even though the set of constraints very often is the same because it's driven by the client, it's set by the client. Different contractors have different experiences and therefore they can promote different methods. I have selected 6 major key drivers that I believe have big impact on the cost and on the cost breakdown. Typically, the aim is to find the right balance between these factors that firstly meets the project constraint and then gives the best value for money for the client. I will go through them one by one and discuss in more details within the next few slides. Firstly, let's discuss pile geometry. Typically, there's more than one right pile geometry that meets the project criteria if we consider that the criteria is achieving sufficient compressive capacity. For compression loads, we can use either deep, small diameter piles or choose shorter piles with larger diameters. If we consider that pile bearing capacity is the key performance indicator and try to find a geometry that achieves this capacity at minimum material volume, we would often find that slender piles with enlarged base would be the most optimal. The saving on the material volumes can be as high as 50, even 70% for piles with enlarged base. And this is because pile ultimate base resistance is orders of magnitude greater than pile unit shaft resistance. So if enlarging pile base leads to such significant material savings, why is it that more than 90% of piles installed around the world are straight shafted? Well, the reasons may be that forming an enlarged base requires stage-wise execution, like it is the case with bored under-rimmed piles. And that may simply be too slow to construct for the method to be economical. Or maybe excessive noise and vibrations, as typically associated with Franke piles, may be excluding this method. I mean, it used to be very common in the past, but not so much these days. It seems that the only method that has a noticeable market share is the steel helical piles, also called steel screw pile method. It actually seems to be gaining popularity. Some of the reasons for that may be the fact that they are very easy and relatively quick to install. They also require relatively small equipment. That means no need for big piling rigs, and consequently the mobilization costs are much smaller and there's no need for heavy working platforms. They also cause little disturbance to the ground and almost no heave nor lateral soil movements. They can be immediately tested and built upon after installation and can be installed also in a wide range of soil conditions. However, they have one big disadvantage, and that is the fact that they're made up of steel, which, as I will show you later, steel is expensive and not very environmentally friendly. Apart from providing capacity, piles are also meant to reduce settlements, and some may actually say that settlement reduction is the most important objective of pile foundations. But to mobilize geotechnical resistance, piles must settle. The amount of settlement required to mobilize shaft friction is typically small, only between 0.5% to 1% of pile's diameter. To mobilize full base capacity, on the other hand, the settlements of between 5 to 25% of pile base are required. In case of piles with large diameter bases, this ultimate base capacity may very often not be possible to utilize during the service life of a structure, and that is because it would simply require too much settlement, and that would be detrimental to the structure. So what can be done with that? I mean, there are methods of improving that load settlement curve for the base to make the soil, to make the load settlement curve stiffer, and examples of such methods are base grouting or base compaction. Both of these methods aim at preloading the pile base during construction and consume plastic settlements, if you allow me to say so that the piles don't need to settle that much during design life. Base grouting doesn't appear to be much used, at least not in Australia. And this may be because it requires additional equipment, additional mobilization to sites, material, and time to perform, which may be offsetting any gains achieved by stiffening up the curve. Even though we know that preloading pile base leads to better pile performance, it doesn't seem to be economical. Another key driver to consider when selecting a pile method is the choice of material. Some materials are cheaper than others, some are stronger, and some are more durable than others in particular ground conditions. So let's compare three most common materials. That is plain concrete, which on the graph is denoted with 0%, because the percentage denotes the steel ratio. Reinforced concrete with different rates of reinforcement, and bare steel, which is the 100% steel rate. To make a meaningful comparison, we need to decide what is the main performance indicator that we want to use to compare the costs, and then we need to normalize the material costs based on that indicator. If we compare cost of materials based on their design compressive strength, we can conclude that the most cost-effective material is lightly reinforced concrete, and obviously that's probably no surprise to you. But what is interesting is to see that plain concrete, I mean, it's twice more expensive if we look only at compressive strength. And that is because concrete is brittle, and it typically, its design capacity has to be reduced by 50% if it's unreinforced. as per the codes like the AS2159, for example. Steel is clearly is the most expensive material from this comparison. Steel is also the least environmentally friendly, and from that slide you can see that concrete, lightly reinforced concrete, can be considered as an environmentally friendly material. Another key decision to be made is about the method of installation. When choosing the installation method, one has to consider many constraints such as the soil conditions, pile arrangement, proximity and impact to other structures, or human comfort. It is generally recognized that displacement methods are faster to install and provide better quality control as compared to replacement methods. Displacement methods also limit the amount of spoil produced on site, which is especially important on contaminated sites. While all displacement methods cause ground movements, that is side heave or lateral movements, some methods can be less disturbing than others. For example, small displacement screw-in methods, such as is used with helical piles, is probably the least disturbing while being relatively fast. Helical piles also often have the highest ratio of pile capacity to the cumulative installation effort. In other words, they require least energy to install to achieve certain capacity. However, as mentioned earlier, helical piles are made of steel, and that is expensive, has high carbon footprint, and can easily corrode in the ground. Moving on, the next key decision is to decide on the size of the equipment. Choosing the right size of the piling rig has a big impact on the cost structure. Large piling rigs offer greater speed of installation, which reduces unit costs of piles. But on the other hand, they're very expensive. They can be very expensive to mobilize and often require heavy-duty working platforms and are less maneuverable on site. Reliability is another factor to be considered, and reliability of constructed piles may vary depending on the chosen method of installation and monitoring. For example, precast-driven piles driven to set under professional supervision and with full monitoring and data analytics will provide much greater level of confidence as compared to a board pile drilled without support and constructed by dumping concrete from the back of a mixer truck. Monitoring of pile driving efforts, for example, thrust and torque, as is the case with drill displacement piles, may also be a very useful quality control procedure, provided that it's properly calibrated on site against existing CPT profiles and ideally also with static load tests. Higher or lower reliability of a particular piling method has a direct impact on the costs. Different methods of installation, quality control, and testing regimes have impact on the geotechnical reduction factors, and as we know, as per our Australian standard 2159, this factor can vary between 0.4 to 0.9, and that's a pretty big range. Techniques that enable better verification of pile performance during construction combined with static load tests often lead to more optimal designs, and static load testing is typically considered to be providing the best quality information about pile performance. If trial piles are installed and tested in advance of the production works, meaningful savings can be achieved by optimizing designs. However, static load tests are expensive to perform, and pre-production trials are even more expensive. Therefore, a right balance between the amount of testing and the reduction factors is a crucial choice that has to be made. So, to summarize, enlarging pile base minimizes material volume. Preloading piles improves their performance during design life. We can also say that concrete appears to be the most economical and environmentally friendly material. We can say that small displacement methods offer a good balance between the speed of installation, quality control, and ground disturbance. Big piling rigs offer faster installation, but are costly to mobilize and require heavy-duty working platforms. testing, especially static load testing, increases confidence that the piles will perform as required. Achieving an optimum solution is not an easy task, and very often improving one aspect leads to deterioration of others. Because there are so many factors to consider, a group of engineers have spent 2 years trying to come up with an installation method which is easy, relatively quick, uses small equipment, yet at the same time produces slender piles with enlarged and preloaded base. In addition, the method enables instant capacity verification of each pile. And this is the method I will demonstrate you next. I'd like to present you the method that may, in many circumstances, offer very optimal and cost-effective solution. This method uses a specially designed auger which resembles a steel helical pile. The drilling process is very similar, it's actually identical to helical piles, so it requires relatively small piling rig to install. Once the auger is drilled to the design depth, the unique construction of the auger enables creation of an enlarged base. It is achieved by pushing helical plates apart, and during that stage, the load required to separate the helical plates is measured and provides instant verification of the pile base capacity. In addition, the ground underneath the pile base becomes preloaded during the process. During formation of the void, as well as during withdrawal of the auger, concrete is pumped through the annulus in the auger and fills the void, and thus a slender pile with an enlarged and preloaded base is formed and using concrete. Maybe let me play that video again for you. So I believe that it can use small equipment just like the helical piles, and as you can see, the installation process is relatively quick. Creation of the void is a fast process, relatively fast. It provides valuable information on the soil resistance within the tip of the pile. That information can be collected and provide direct feedback to the piling rig operator. So if, for example, the auger has been drilled to a certain depth and during void formation, the recorded load has not achieved the desired outcome, the rig operator can revert back to drilling, drill deeper, and do the process again until the recorded load meets the design criteria. This method of pile formation has successfully passed initial field trials, and as you can see from the photos herein, it is possible to create slender piles with enlarged base using this process. The picture on the right shows a pile that was performed in sand and using grout, and therefore the size of the base is actually bigger than intended. Nevertheless, the idea has been successfully validated in different soil types. Let's look at the economics of this new method. If we wanted to install a 10-meter deep pile with 250 mm diameter shaft with 750 millimeter base, we could probably use a 30 to 40 ton piling rig. The productivity would be driven by the pitch of the helix, which in case of helical piles is typically 30% of the diameter of the helix, and would be also driven by the rotational speed of the rotary head, the RPM speed. Assuming conservative approach, that is, let's say that the rotary head would be installing at about 20 RPM speed and the pitch of the helix is 200 mil, that would enable creating about 35 piles per day with the anticipated cost of about $60 per meter. Key advantages of this method include smaller equipment and therefore lower mobilization costs, much less material required, increased reliability, minimized ground disturbance, no vibrations, it's a screw-in process, capacity verification for each pile. Pile technology enables a direct measurement of the force required to create the pile base, which together with constant torque monitoring can provide valuable information. And data from all piles across the site can be analyzed further using machine learning to generate a site risk profile. And this site risk profile modeling is at the very early development stage, but this is why the letters AI appear in the pile name, which stands for artificial intelligence. So let's do some cost simulations. I have selected a typical 5,000 square meter building with an equivalent UDL load of 50 kPa, which equates to approximately 250,000 kilonewtons of design load. And I will compare 5 conventional piling methods to see how do they compare cost-wise. And at start, I would like to compare it based on this soil profile. So there's 5 meters of compressible soil underlain by medium dense sand. It is assumed that bedrock is at about 35 meters below the surface. Now, the methods that I dared to compare are the conventional continuous flight auger pile, drill displacement pile, timber piles, precast, driven piles, steel helical piles, and the new piling method. The left graph shows a comparison between a normalized unit cost of each piling method. It is basically cost of a single pile divided by its design capacity. So, because obviously all these different piles, they have different capacities and they have different costs. So therefore, there's a need to normalize the unit cost, and that's what the left graph is showing. It's basically showing a normalized unit cost. How many dollars does it cost to carry 1 kilonewton of building load? From the comparison, you can see that the drill displacement piles have a pretty low unit cost compared to other methods, and that is because the ground conditions are quite favorable in this case for this method. Drill displacement piles are very quick to install, and if can be founded in medium to dense sands, they can also achieve pretty good load capacities. However, drill displacement piling methods require heavy piling rigs, and therefore the project has to be of sufficient size to amortize this cost across the entire project. In the middle, in the right graph, you can see the total costs, how they compare for different methods. And you may notice that driven piles here appear to be quite expensive if compared to drill displacement piles, and that is because in this particular case, the depth to rock is quite significant. CFA piles can't rely much on base bearing and because of the depth to rock, and therefore require deep socket, and that is why in this case they're the loser. What is interesting to see is that even in ground conditions that favor drill displacement piles, the new piling unit costs are still cheaper when mobilization costs are taken into consideration. The overall costs are predicted to be much lower than for the drill displacement piles. You will most likely ask now, what if the bedrock is closer to the surface? And that's what we're going to try to find out on the next slide. If we change the ground conditions and assume that the bedrock is about 10 meters below the surface, then the comparisons look different. Obviously, in such scenario, the driven piles don't have to be drilled that deep. They can achieve their full structural capacity at pretty much 10-meter depth once they hit the rock. And hence, their normalized unit cost becomes definitely better, lower. You can see from this comparison that all methods, except for helical piles in this case, offer similar unit costs. And it's the mobilization cost that make or break which piling method turns out to be the most cost effective. However, even in such ground conditions that are ideal for driven piles, the proposed new piling method offers similar unit costs. while at the same time it offers other benefits like no ground vibrations and smaller equipment. Okay, so we know that depth to rock is an important factor when it comes to choosing the most economical method. So let's do a bit more sensitivity analysis on that. From the graph on the left, we can see that if the compressible soil is underlain by medium dense sand, then the drill displacement piles and the new piling method offer the best unit costs, normalized unit costs, provided that the depth to rock is greater than about 15 meters. If it's less, then the driven piles become much more cost effective. Well, maybe not much more, but they become cost effective. On the other hand, if the compressible soils are underlain by very stiff clays, which is the case shown on the graph on the right, then the drill displacement piles stop being that economical. And the reason for that is that drill displacement piles cannot be socketed indefinitely into very stiff clays. They are typically socketed maximum 3 to 4 meters. And because it's very stiff at much capacity as compared to medium dense sands. But in such conditions, the new pile method appears to be very competitive, provided that the bedrock is deeper than 15 meters below the ground surface. If the bedrock is closer to the surface, the unit cost between driven piles and the new pile methods appear to be comparable. It is anticipated that this new piling method could have a wide range of applications, including buildings on compressible soils, where small equipment, no vibrations, and low unit costs, excellent performance would make it an economical solution. High uplift capacity associated with piles with enlarged bases would also make them attractive for expansive size, where tensile loads can be problematic. Road embankments could also be economically supported by these new piles. Because these piles have minimized volume, they would be causing much less heave, less lateral soil deformations, because much less concrete is pumped into the ground to achieve the same capacity. The use of small equipment would also provide great benefits. On typical road upgrade projects, rigid inclusions are designed under approach embankments to limit settlements. These works very often have to be performed in multiple stages with only limited amount of work per each mobilization, and reducing mobilization costs could have significant impact on the costs of these projects. The fact that these piles can be installed with relatively small equipment means that it would be possible to install them in raked configurations as well. Similarly, how helical piles or micropiles are often used. This in turn would offer another range of possibilities for this technique. If we still have some time, and I believe that we do, because I managed to get under 30 minutes, which hopefully managed to keep you up. I would like to present you a foundation design optimization tool, which we use ourselves, and we made it available just yesterday to the community on our website. All you need is to type pile.solutions/design into your web browser, and it will take you to this web app. The app performs pile design capacity calculations using the latest LCPC method, which is the French method, based on a CPT soil profile. The user has to define or upload a CSV file with CPT data, and then you simply need to, once you have uploaded the CPT profile or manually defined it at random intervals, the user has to specify depth to the groundwater, a CPT cone factor, which by default is 0.8, and depth to the unstable zone, which it has to be decided by the user what he considered as unstable zone. And that unstable zone is then not used for capacity considerations. After clicking submit, the app performs interpretation of the CPT profile using Robertson 2010 equations to derive soil behavior type index and normalized con resistances. And these can be viewed by changing the tabs here. You can see the raw data, what's the tip resistance, what's the friction, and then the normalized plots. But you can also click on data table, and that will take you to this table where you can view every single data that has been input and processed by the web application. So once you have defined the soil profile, we move on to the foundation design tab, where we basically can compare 4 different methods. The user has to define what ultimate load capacity is required, and that is the unfactored capacity. And then for each respective method, define the shaft diameter. Once that has been input, plots are then plotted for each type of pile, showing how the capacity increases with increasing depth of the pile. Then you can move on to the report section, which will take you to a comparison table. And in that table, you may see that for different types, there are different depths and different volumes of piles to achieve the same load capacity that you have defined earlier. In the near future, we intend to add a simple cost estimating module as well that will enable you to see what the price differential is expected depending on the choice of the piling method. We also intend to launch a settlement calculation module in the next stage of the web application. That then you can plot those graphs that I showed you previously by yourself, comparing different methods with mobilization costs and all this cool stuff, I hope. So thank you. That's about it, what I wanted to show you. I hope you enjoyed it. I tried to make it concise, and hopefully you have some questions that I hopefully will be able to answer.
Thank you, Adam. That was really interesting. Can I just ask one? Do you leave the steel in the ground, or do you take the whole pile out and just leave concrete?
So the auger is extracted from the ground, and steel can be introduced afterwards, just in the same way as typical CFA piles or drill displacement piles. But the auger is an auger. So it goes in, creates the void in the ground, and it's pulled out, and it's screwed out of the ground and used on the next hole, on the next location.
Okay, no, that's what I couldn't get. So yeah, thanks for that. Particularly with the anchor.
Yes, so maybe with that, there is a possibility of actually introducing the Rio bar before installing and having it connected at the tip of the at the bottom of the auger. So it would be sitting inside of the hollow section, and once it's drilled all the way down and the helices are separated during extraction, it would basically stay in the ground. So for rakers, for anchors, that would probably be required, because introducing steel reinforcement and raked CFA or full displacement drilled piles is very difficult, if not impossible. So, but using Rio bar inside is possible as well.
Cool, thank you. We have a question. What's the typical maximum axial capacity of the pile?
So it will depend on the actual size chosen. So in these comparisons, I showed you pile that has 250 millimeter shaft diameter with 750 base, and its capacity was calculated in these particular ground conditions at 662 kilonewtons, and that's a factored capacity. But it can be more than that. It's pretty much driven by the structural capacity of the shaft and then how much resistance can be mobilized underneath. And if you look at helical piles, I know that they can be installed up to 600 mil shaft diameters. So quite significant loads could be actually taken by those piles.
Right. Question from Sid is if you have a very narrow column, how do you ensure enough cover to reinforcement?
Well, that would be similar as dealing with micropiles, which are very often reinforced. They have to be reinforced, and it's the same problem which has been discussed and solved many times. I mean, yes, we have to ensure cover, but if we use, for example, grout, we can reduce that cover because typically grout has better properties in preventing corrosion. If you look at the guidelines for micropile design, they typically allow much smaller covers. But again, that would have to be considered separately. I guess for compression piles, the concrete does most of the job. To allow for eccentric loads and bending moments, there could be a possibility of introducing a short pipe section at the top of that slender pile that can be galvanized, and there would be no risk of damaging that galvanization. And in that case, there's not much cover is really needed. And that pile section, well, if you consider how the pile is working in the ground, typically bending moments become negligible within 10 diameters of the pile from the surface. And because this pile is slender, it's only 250, it would be sufficient to introduce 2.5 meter pipe. And it's easy to handle on site. It can be done by an offsider pretty much. So no need for cranes or expensive equipment.
Right. Okay, I actually have a question from Magda. What is the operational readiness of this? Is it already available?
It is not yet available. It's work under progress, but we believe it can be commercially available within 6 to 12 months.
Right. And can it be used in shallow water for offshore piling?
Well, it would be, I guess, similar challenges as is the case with CFA piles. I mean, it's an open hole that is grouted. So once you get out of the ground and you have water above, well, you can probably grout it all the way up, but without seeing what you're doing, I guess I'm not sure about that. I mean, that would probably require further research and more brainstorming sessions.
Yeah, it does seem a bit pushed too far. Okay, we have sorry, I'm just trying to read these questions. Are there limitations of the pile rig in terms of penetration due to limited torque? Do you need to pre-drill?
Well, it would be very similar as is the case with helical piles. As you know, helical piles, they kind of suck themselves in. They advance themselves by kind of pushing off the soil above them. But if there's a quick transition in ground consistency, for example, very soft clay underlain suddenly by very dense sand, augering can occur, obviously. And in that case, well, augering may be required to advance the pile deeper, but it's still possible to advance, only that in such case there's a little bit more disturbance of the ground above, which may not necessarily be completely damaging the performance, because it relies on the bottom really. So, and the bottom hasn't been destroyed during that process, but there would be no verification of that capacity during the process of expanding the helices. So it can still be formed, but there would be less data from monitoring of the rig to confirm that the capacity has been achieved.
Okay. What's the minimum distance between two piles?
Well, that's that would be similar as it is with the helical piles. I guess further studies are still required to assess the impact during formation of the base onto adjacent piles that have been previously formed, but that stroke is fairly limited. It's pretty much the height of the bulb is equal to the diameter of the bulb. So that expansion, spherical expansion problem, if you could call it, is fairly limited. But yeah, I guess there would be some constraints to that. I can't answer exactly that that question at the moment. We haven't progressed with the research that far yet, but it is definitely on the list.
When you spread the helix out, what's the preload that's applied to the soil at that stage?
Well, it's basically the force that we need to apply to open the helices, and that is driven by either the resistance of the soil under the bottom helix or the resistance of the soil above the top helix, as you can imagine. So the top part draws resistance from uplift resistance of the external pipe with the helix. So there's skin friction along the shaft, and there's also bearing acting against the upper helix. In both cases, void can be formed. If the bottom helix, if the ground under the helix yields and the bottom helix moves down, we know what the plunging failure of the base is. If the upper helix goes up, we still measure the force, so we know what's the lower bound of the resistance of the pile, because we know that it's more than what we use to expand the helixes.
And in clay soils, is there a minimum time to wait after piles installation to ensure undrained shear strength gained?
Undrained shear strength gain doesn't have to be considered really in the design, and it isn't. It typically isn't when you design drill displacement piles and cohesive soils. The formulas are dependent on the CPT cone resistances typically, and that what drives the design. So I'm not sure if there is any such requirement. Yes, the rate of expansion will definitely have impact on how the pressures within the soil dissipate, how quickly. But ultimately, that should not be a driving factor.
Cool. I think that's the last of our questions. I'll give it a few seconds to see if anyone else wants to ask a question. While I do that, I just want to remind everyone that the AGS presentations are running weekly, so they're on the AGS website, so please have a look at that. Okay, well, I think we're how does the pile respond under earthquake load?
Well, it will respond as any slender pile in the ground, I guess, or at least that's what I believe. We haven't done such simulations yet. Again, it's on the to-do list, but slender piles, they follow the ground movements, and if the more slender the pile is, the more movements it can typically accommodate. It's actually a bit opposite to what some engineers think, that enlarging diameter of pile increases its strength to bending. Well, it does if the bending comes from external loads, but if it comes from lateral soil movements that the pile cannot prevent from happening, it basically has to follow the movements, then the lesser bending resistance of a pile, the more curvature it can accommodate during those that occur due to those lateral soil movements. So obviously, yeah, that's, I'm not sure if I answered the question.
No, you did better than me, so. One from Kamal. Do you have a comparison of machine learning and actual static load testing?
No, not yet, not at this stage. It's under development.
Okay. All right then. Well, I think looks like those are the questions. So, Adam, I'd like to thank you for taking time to present to us tonight.
Thank you.
And thank you to the AGS members who joined tonight. Thank you very much. Close this down for the